All right, so today we'll be covering Chapter 6, which is Introduction to Internet Protocol. So basically, we'll be talking about two major topics today. The first is going to be TCP/IP, which is a pretty big topic. The second topic is going to be data encapsulation. We're going to go into that some. So certainly, starting off with a history of TCP/IP. Basically, first version was somewhat released in 1974. Not a history class or anything. Just make sure that you understand it was originally used for ARPANET. And the division between, so the first version was technically TCP, Transmission Control Protocol, and it was divided into TCP and IP in 1978. And of course, the primary purpose of this was to share research data across institutions that were separated geographically. So we didn't have the internet back then, but certainly ARPA and later DARPA certainly needed some sort of a network to be able to share that communication. So that's basically what this is all about. And the model that the DoD had for this is very similar to the OSI model. Now looking at this, who can tell me the primary difference between the two? So where do they differ? So they differ primarily up here. So basically the process and application and presentation and session in OSI is just the process and application in the DoD model. Apart from that, they're pretty much the same thing. Network access is a little bit different, but for the most part, just understand, we're talking about the differences. We're talking about the DoD model doesn't distinguish a session from presentation from application. Does that make sense? But like I say, basically the same model. The other difference being data link and physical, not being separate on network access. And if you go back to why, it's not really developed for the purpose of having billions and billions of devices, developed for having point-to-point, basically. So, kind of looking at this, what we have is the different protocols that are associated with each of these different layers. So process and application, it's going to be anything that an application might use to communicate. For example, Telnet. If you're on a router, wanting to configure the router, you could use Telnet. Wouldn't recommend it in, current age, but it's theoretically possible. We're going to talk about these different protocols in a little bit here. But basically, let's understand what these different protocols, how they relate to each layer. So, of course, internet, IP, address routing, reverse address routing, all that's going to be included in the internet. And, of course, network access, we're talking about the physical transfer. It's going to be all about the different standards associated with that. We're talking about TCP versus UDP in a little bit as well. So, like I said, just kind of understand this is where all these layers are happening. Think about this model right here. So process and application, all about what you're using, how you directly interface with stuff. Host to host is about how that data sort of, in a way, is transmitted to you. Internet, of course, being the standards to be able to communicate on the network, and then network access being the actual physical connection there. Does that make sense? All right, so talk about the different process and application layers, and basically, these are all going to be logical ports. You think about a switch, it has ports maybe 1 through 48, for example. We're not talking about the physical port with any of this. We're talking about a logical port. So think about how we do routing. Route with a port, that's part of it. So for example, the Telnet protocol is going to be for terminal emulation. Like I say, it's primarily what was primarily used to, say, configure a device remotely. For example, if you use a Raspberry Pi and you do a headless install with it, you're probably using SSH, because if you're using Telnet, it's insecure, no encryption. So that means anyone could theoretically intercept what you're doing, and it's not going to be very useful. But do make sure that you memorize these port numbers. If they're up here, it's very fair game for an exam. So, because, let's face it, it's also fair game for the Network Plus exam. So make sure you memorize the port numbers. For Telnet, it's going to be port 23. But also, the most important thing about Telnet, remember to use SSH instead of Telnet. It's important to know about Telnet because if you're using legacy systems that don't support SSH, well, legacy systems have their own set of problems, of course, but it's still important to understand the basics of it. FTP, of course, is going to be file transfer protocol. You've probably at some point used the file transfer protocol server, where you downloaded files, you can browse a directory, all that sort of stuff. two ports it's using, TCP 20 and 21. Of course, like with the telnet, there's a secure version that uses encryption, which is preferable for almost anything you can imagine. There's some slight exceptions. If the data is freely given out anyway, and you're wanting to support legacy stuff for some reason, then you would use FTP. But for most other things, you're going to use SFTP. And the main difference is that it uses SSH to encrypt. So it's going to be using TCP port 22 for that. Like I say, very similar in functionality. You know, an end user wouldn't notice a difference, but just understand it's using encryption, which is, of course, superior for most things today. Of course, we have trivial file transfer protocol. This is going to be where you have something else that provides the directory access. So when I say something else, there's some other way that you keep track of where the files are. It's not going to be done through this protocol because it doesn't have a directory built in. So if you navigated to a web page, you would have to navigate to the exact address of the file as opposed to navigating to a parent directory and then navigating to it. Does that make sense? So it's going to be port 69 on UDP. So that's basically what it's using there. I want to talk a little bit about TCP versus UDP. So we've got our TCP guy here, and we've got the CHAD UDP here. So basically what this is talking about is the CHAD UDP isn't really establishing a connection. It's connectionless. Okay, that means that we're not having a huge header that establishes a virtual circuit. It basically just sends the packets. You either get them or you don't. You know, whereas we have this TCP. It's kind of funny. It says double text girlfriend for acknowledgement. Okay, so what we're doing is we're sending a synchronized signal, then we're sending synchronize acknowledge, then we're sending acknowledge. Okay, that's not an efficient way to communicate, but it could be needed because if we're doing communication that we want to ensure is received without error, definitely going to use TCP. If we're doing something that requires real-time communication, almost always going to be UDP because it's a lot lower overhead. And like if you miss a packet in a VoIP call or you miss a packet in a video call, what happens? You just miss that packet. It's not like if it's added later, it'll make more sense, you know? That's why we have things like UDP. Now I had to kind of adjust the language just a little bit. There was a little bit of profanity on here, so if you see some bad edits, that's why. Kind of keep that in mind. So yeah, basically, like I say, this is going to be for most things today because we want to ensure that it's received without issue. But for anything synchronous, it's almost always going to be UDP. There are some exceptions to that, of course. You know, like if you're sending a text message over a LTE or over some sort of data network, maybe Wi-Fi, definitely using TCP. You want to make sure it's received. But if you're sending something real time, you know, UDP is where it's at. Any questions about this? All right, never forget the difference between TCP and UDP. Okay, try to find something to be a little bit humorous to kind of illustrate that. Hope that worked. Talk about simple mail transfer protocol. As the name would imply, it's to send an email. So if you want to send an email, you could use the simple mail transfer protocol. It's going to be over TCP port 25. So why do we want to use a TCP connection to send an email? Someone throw me an answer. Yeah, exactly. You want to make sure the email is sent. You know, how do you do that with UDP? You don't. You know, it's okay to have an email send a little bit slower. We're talking, you know, a couple milliseconds for small text, you know, email. That's okay. If it's not sent at all, that could be a big problem, though. Of course, POP v3 is going to be receive email. And this is more of an outdated protocol. SMTP is pretty outdated as well. But a lot of organizations actually block post office protocol because it's outdated and doesn't really have a lot of security features or anything. Just understand it's over TCP port 110. Something that's not outdated is IMAP. Okay, so we've got Internet Message Access Protocol. It's going to have lots of additional sort of security controls. This is where if you set up email on a mobile device and your organization is the manager for the email account, they can set certain security requirements like maybe you have to enable remote wipe. so that if your device is ever lost, you can go in and remotely wipe it. Does it mean that the network administrator is going to remotely wipe your device for fun? Hopefully not. It's theoretically possible, though. I don't know of many cases of that happening. How do we avoid problems with that? Back up your stuff. That should be pretty self-explanatory. Going over TCP port 143. Who's used a remote desktop connection before? Okay. So basically, you're using RDP for that, and as the name would imply, you're remotely accessing a system. Now, this protocol is somewhat proprietary. I wouldn't necessarily call it a proprietary protocol because, by definition, it's not purely proprietary. But it's also not exactly an open standard either. So if you're using something like Linux, probably want to use some other connection than RDP because, let's face it, it's a Microsoft protocol. Apple has their implementation of it, which is pretty much compatible. But, just understand it's using TCP port 3389. Now, this is kind of an interesting one. Why might we want to use TCP for remote desktop connection? Because you could argue that if you drop a frame in a remote desktop connection, who cares? You're already on to the next frame. Why might we want to use a TCP for that instead of UDP? Who wants to take a stab at that? You think Microsoft just didn't know what they were doing? No, they want to verify that whatever you're sending to the computer is what you intended to send to the computer. Imagine you sent a command and it received a different command. Some problem in transmission. A lot of things could go wrong. TCP is going to prevent that. UDP would not. So imagine you're connected to a server and somehow or another it mistakenly thinks you send it a shutdown signal. Is that going to be a problem for your organization? Probably will. So that's sort of the things that you want to think about. It's not just about performance and speed. It's also about making sure we're sending the correct things. Like I say, on a video call, not an issue. Voice call, not an issue. But for most things, we're going to be using TCP. All right, so the book doesn't do a great job talking about TLS and SSL. So basically, I'm going to add a little bit more to what the book said. Both for encrypted web communications. I don't know where they got their port numbers from. Never really seen anything use those, but whatever. I would argue it's going to use port 443 for the most part. There are some exceptions to that, and I'm not doubting that, but to understand, we're talking about TLS and SSL, we're talking about port 443. It's going to be a lot more secure if we're using TLS than SSL. Basically, the history is SSL was developed by Netscape Navigator. You guys remember Netscape? Okay, it's SSL. There have been some additional versions. So basically, it was open sourced around 2000 or so. Don't quote me on that year. But just understand that it's an open source standard. But TLS has a lot better security. It's going to be faster to use. I think it's also open source as well. You guys remember the Heartbleed vulnerability? Who could tell me about the Heartbleed vulnerability? Was that TLS or SSL? It's an SSL vulnerability and basically broke encryption, so that could be a big problem. All right, and of course we're talking about encrypted web communications. We're talking about you go to a website, it's using one of these two, hopefully TLS in 2021, but that's an opinion, maybe for SSL. Session Initiation Protocol, commonly referred to as SIP, and basically it's going to be used for video and voice calls, really anything synchronous. So with this, developers who are using this protocol have an option of using either TCP or UDP for this. There are advantages and disadvantages to both. If you're using messaging, which one do you think you're going to use? Probably TCP. What about a video or voice call? Using that CHAD UDP. So those are basically your options there. Just understand that sometimes there's an option to use TCP or UDP. Sometimes there isn't. It really depends on what the standard says. So, like I said, there's a lot of reasons why you may use one or the other, but it's really a personal decision and really a logical decision as well. Just kind of use common sense and you'll be in a lot better place. RTP, of course, can be for VoIP calls as well, and it's going to be using both UDP 5004 and TCP 5005. So, somewhat you have an option, but mostly TCP is going to be used to initiate the call, and once the call is going on, you're going to switch over to UDP, mostly. Obviously, there's going to be exceptions to pretty much everything in networking, but you're talking about the general sense, what's going to be what you know, TCP to initiate, because we want to make sure we actually initiate the call. And once it's initiated, whatever goes, goes. SNMP, it's going to be used for a lot of router-to-router communication, router-to-switch communication. Like I said, anyone get a chance to run Wireshark on their personal network? It's a fun thing to do. You'll see a lot of SNMP going across where it's doing a bunch of synchronized acknowledges, it's doing a bunch of who is this, that sort of stuff. It's cool to see. It's all SNMP. You can also, of course, manage various network equipment with it. It's other use. It's going to be on UDP port 161, which is somewhat interesting. It's on UDP, but if you think about it, it's just making sure that it gets the signal out there. It doesn't want to have a time to live or anything like that it has to worry with. Some more process application layer things to know. Secure shell, this is a very important one. Secure shell, of course, can be an encrypted way to communicate. So if you wanted to do an SSH connection into something, you can. It's primarily going to be text-based, but it's not just used for text-based communication. It's really a pretty wide range standard. It's going to be over TCP port 22. Make sure you remember that one in particular, but make sure you remember all the port numbers. It's not a fun thing to remember, but luckily there's only about 20 of them. HTTP, who can tell me what HTTP is for? It's web pages. Hopefully you guys know that. So anytime you go to a web page using HTTP, it's going to be going over port 80. TCP, of course. All right, HTTPS, obviously it's using encryption there, so it's going to be port 443. So pretty straightforward for that one. Network time protocol, this is an interesting one because basically what we're doing, communicating with some sort of a time server, and as opposed to using, say, HTTP or HTTPS, you got a dedicated protocol for it. It's going to be used for a lot of different things. Think about time-stamping anything. You go to a transaction, timestamp the transaction, probably use an NTP. It doesn't have to be NTP. No law saying it has to be. Actually, there might be regulations about that. But anyway, let's understand it's going to be used to synchronize clocks. It's going to be over UDP port 123. Now, why are we using UDP here? Why not TCP? Don't we want to make sure we have the time? Not exactly, because if we don't have the time in the application, it's going to ask again. And it's going to keep asking until it receives the time. So we don't have to have that sort of redundancy where it's built into the transmission standard. Opposed to that, I want to use UDP because it's fast. Okay, let's say that we have something where milliseconds are an issue. If we're having to be competing on milliseconds, obviously we don't have a header that's 60 bytes long. That'd be a pretty bad problem. So use UDP to avoid that. That's why we're using UDP here. All right, we've got LDAP, Lightweight Directory Access Protocol. So LDAP, of course, can be used for directory access across an organization. Think about something like Active Directory. It's compatible with LDAP. Think about something like Novell, whatever their directory is called. Things like NetSuite or something weird like that. It's also using LDAP. So basically, it's a standard to sort of allow people to communicate whatever directory access they have. It's going to be widely used on Windows in particular. Think about things like printers. Think about things like user accounts. Think about things like what all that's tied to. It all goes back to relying on LDAP for that. So, of course, that's going to be port 389. Obviously, it's going to use TCP. Secure message block. So this is going to be a Windows standard, but I'm going to caution you and say that it's probably not the most secure standard. Having said that, it's also available in Linux. There's an open version of it. It's called Samba. It's mostly compatible for most things, not 100% of things. But basically, it's going to be used for sharing of devices. And like I say, it's not the best way to do things, but it is a way to do things, and it is used some places. So make sure you understand it's TCP port 445 for that. So, it's kind of like an alternative to FTP, but not really. It's a lot more decentralized than FTP. It's not a central server by any stretch. It's just, I have these files, here you go, that sort of thing. DNS. Who can tell me what DNS is? Anyone? Ben, what's DNS? Exactly, resolving domains into IP addresses. It's the primary use of it. There's other uses as well. I've already covered them. This is where you have the option to use either TCP or UDP. It's going to be port 53, regardless of what you use. So just make sure that you understand that it's going to be over that port, but you have the option to use UDP or TCP. Of course, the primary reason for that is some applications are going to be able to have the air checking built in, others are not. So you got an option there. If you want to save a little bit of bandwidth, save a little bit of speed, UDP. If you want to make sure that you got the address, TCP. Of course, we have DHCP. So DHCP is going to be used to dynamically assign an IP address to a host. And beyond that, you could also theoretically use it to assign a static IP address to a host. There are certainly cases where you'd want to do that. They do it based on MAC. It's also going to handle any sort of reservations, anything like that. It's going to be over UDP, ports 67 and 68. All right. That's a lot of stuff to know, isn't it? So, like I said, just make sure you understand the basics of what each layer does, as well as its port. I'm probably not going to ask you whether something's TCP or UDP, but make sure you understand the difference between them. I would ask you more of a general sense, what do you use each for? Does that make sense? The port numbers are important to remember because pretty much any certification you take that touches networking, you got to know them. So therefore, you guys got to know them. Pretty straightforward. So kind of moving out of the application layer, moving down into the host to host, this is where we're really doing a lot of the connection, getting it ready to be transmitted. So it's going to be using either TCP or UDP, which we've talked about some in here. Like I say, think about not the Chad. Think about him. He's sending a synchronize, acknowledge, and acknowledge. Got a really large header, anywhere from 20 to 60 bytes, and that's pretty big. Think about how big a byte is. Imagine each packet, which by the way, the data is not going to be larger than like a megabyte or something. Probably much smaller in most cases. Imagine how much overhead that is. Is that a lot of overhead? That's a lot of overhead. Like I say, if you got all these different things in here, I'm not going to test you over the parts of a TCP header, but just understand, there's a lot of stuff in here. So, just make sure you understand that. Any questions about TCP? All right, contrast with UDP. UDP, of course, can be very lightweight. Doesn't have a very large header. Much smaller header. It's not establishing a virtual circuit. It's connectionless. So we're thinking about what is UDP? It's going to be where you don't care about reliability, or you have another way of ensuring reliability. Because basically, it does not have verification built in. Has a checksum, has a link. That's about it. So going back to some of the different protocols, a lot of protocols have it built in to have checking externally. And if you added another check, what's that going to do to the speed? Exactly, it's going to slow it down. In general, we have a network, we want to have it be fast, robust, reliable. Okay. Adding in additional verification, we already verified something, is pointless. So I'm just going to kind of briefly go through this. Like I say, TCP is going to be very organized, it's going to be very header heavy, it's going to have a very large header. It's going to be reliable. It can verify that what it's sent was received. Lots of acknowledgments and stuff happening. Think about the guy who sends synchronize and acknowledge to his girlfriend. That is TCP. All right. I'm not going to ask if anyone in here does that, but I hope you don't. So, and I'm sure you don't. Contrast, UDP, like I said, unreliable. And I wouldn't necessarily call it unreliable. Personally, I think it'd be very reliable for what it is. It's less reliable than TCP, but to call it unreliable, I think is a fallacy. Because what's the definition of unreliable? Think about reliable. It means it can be relied upon. You know, it's something that we have inputs, we know what outputs are going to be. Do we know that TCP will reach its destination? No, of course not. We just don't have a way to verify that TCP reached its destination. So therefore, I wouldn't personally use the term unreliable when describing UDP. In theory, it's no less reliable than TCP. Does that make sense? It's going over the same circuit, you know, for goodness sakes. We've got a cable at the physical layer going over the same exact cable. No more or less reliable, it's just we can't verify that it was received. Unverifiable would be a better word to use than unreliable. Does that make sense? Another aside about the book, kind of funny. Did you guys catch where they're talking about FTP? And they said if you're sending an email with an attachment larger than 10 megabytes, is that pretty funny or what? You know, what would we more likely use instead of FTP for that? Now, obviously the limit's going to be much closer to say 25 or 50 megabytes in 2021. But assuming we're at that limit, what are we more likely to use in FTP to submit a file that's larger than the email's capacity? Starts with C. It's up in the sky. Cloud. You know, it's built into most email platforms. The book's kind of funny talking about you got to use FTP. No, you don't. Let's talk a little about the different internet layer protocols. So what this really does is it's going to help us sort of standardize routing. Now, why this is important is because imagine you're an application developer and you want to have network connectivity. Okay, isn't it a lot nicer to reference an existing API that handles all this as opposed to having to make your own for each application? Let's put it in terms of the user. Imagine you're a user. Do you want to have to install different ways to connect for every application you use? Absolutely not. Standardized routing is the main thing here. We're also going to cover IP, Internet Protocol in this case. ICMP, just a little bit, talk about what it is, why it's used. Address Resolution Protocol and Reverse Address Resolution Protocol. They sound really intimidating, but they're not intimidating. So, IP, as the name would imply, it's going to route using IP addresses. So we know what an IP address is. We've got IPv4. That's what we're primarily talking about up to this point. Basically got 3 characters, 3 characters, 3 characters, 3 characters. And it's going to route based on this address. So really straightforward. You know, 12 characters gets you anywhere. Of course, what we haven't talked about a whole lot is local versus external IPs. We're going to cover that in the, I think, Chapter 7 or Chapter 8 when we talk about IP addressing. But for now, just understand we have local addresses and we have external addresses as well. Of course, the good news with IPv4, this is a limited number of them. Obviously, not everything has to have a unique external IP address. We're going to use network address tunneling to address that. But basically, all we're doing here is just routing using IP address. So you can see on here, we've got the source IP and the destination IP address. That's what we're talking about in this context, just these 2 things right here. Does that make sense? Really straightforward there. ICMP, like I said, it's a very useful protocol, especially as a network engineer or network admin, whatever your title is, because it's really going to help you with several key things on a network. Most commonly, you're going to be using something like a ping to verify that a connection can be received or established, or a trace route to see where exactly the connection goes. More commonly, on most devices, you'll hear that referred to as a trace. Trace route's sort of like the full name that no one uses. Does that make sense? Just make sure you understand trace route are the same. But there's a lot of different things you could do as well. Common events you may receive, destination unreachable. What does that mean? Something's unreachable. It means we can't get to it. It means it's powered off. Maybe it is unplugged. Maybe it is whatever. Can't establish a connection to it. Get a destination unreachable. Buffer full. Pretty unlikely to run into this. If you're using really, how should I put this politely? If you're using really low quality hardware, maybe old, like 20 years old, or maybe just hardware that has like a memory leak in it or something, and for whatever reason, the memory is full, you get a buffer full, meaning that you'll have to try again later. That's what we're talking about there. Like I said, address resolution protocol. sounds really intimidating, but it's not. All you're doing is you have an IP address and you're turning it into a MAC address. So, in here, and this is basically what the communication looks like. You have one device who's asking for the physical address of another device, and I would say this would be more likely to be a router than a end host, but whatever. So basically, it's saying that it's going to give you the IP or the MAC address back. So obviously, it's not going to happen across networks. It's going to have to be on the same collision domain, and there's a lot of different reasons for that. The most obvious one being MAC addresses are not ever going to leave the. Well, let me rephrase that. MAC addresses should not ever leave the local network. Does that make sense? Basically, that's all we're talking about there. Then, of course, you have reverse address resolution protocol. And this is going to be a little bit more interesting. So this is where we're going to have some device that doesn't have a storage disk. And if we don't have a storage disk, well, let me rephrase that. We don't have a writable storage disk. We could certainly have storage media that's not writable. So, this is going to be for something like, I don't know, some sort of embedded system where it's not writing anything to any storage. It has maybe a read-only memory, something like that. Okay, if you have read-only memory, how are we going to write a dynamic IP to that? How do we do it? We don't. But it's going to know its MAC address because MAC address is a physical hardware address. It does not change. So basically use reverse address resolution protocol to say, I have this MAC address. What is my IP address? And it's going to return that IP address to you. So kind of a cool technology. But like I said, it's not really that complicated once you understand what you're doing. So basically it's just going to ask for the IP, and it's going to return that to you. So, does that make sense? Any questions about it? I talk a little bit about data encapsulation. Just kind of wrapping the chapter up here. Basically, data encapsulation is going to be the actual process of sort of moving the packet across a layer. That's where we add all the different things to it. We'll talk about that. But what we're doing here is we're using protocol data units. And these protocol data units can be really anywhere. They don't have to be in the header. Almost every case we're using them, though, they're probably going to be in the header. Why do we want to have them in the header instead of just in some random place? Well, the main reason is if you have a bunch of different packets and just various information all scattered around, it's going to take a lot more time to figure out what's going on. So, kind of keep everything nice and standard. And this is really where a packet shaper would come in. So, packet shaper could sort of grab the packets and sort of change them around to make sure that they're all matching what the organization expects. So, it's just basic encapsulation process. We know that we have stuff happening in the network layer, frame layer, and physical layer. So basically what it's doing is adding the TCP information in the upper layer, to be all this sort of application stuff. IP header, you can tell it where to go. The network, we've got the LLC and the MAC. We're going to talk about that in a couple chapters here. And then lastly, the physical converts it to binary. So really straightforward there. So these are the different steps. These are pretty important steps. Make sure you understand them. This is definitely the most important part of data encapsulation. So what happens is we have the application layer, we have the session and all that. We're going to convert all of the user data to get it ready for transmission. Okay? So whatever the user data is, we're going to convert it. That's what we're happening first. Then we're going to segment it, put it in nice little segments, and establish that reliable connection. Now, obviously, based on this, what do we know is this is going to be in? Exactly. It does not happen inside of UDP, and not in this fashion. Basically, UDP is just putting it into packets and, make sure we have the address. Okay, so then we convert the segments to packets, and we add the logical address. So that's what we're doing next. Once we've done that, we're going to convert the packets to frames for local transmission. This is local transmission to the router. Okay, so then once we got it to the router, it's going to be converted to bits. And once it's converted to bits, of course, we go out. That's basically what we're doing there. So let's make sure you understand this. Are there any questions about data encapsulation? So it's an important topic. But basically, this is what it looks like. So we've got the segment it has the data inside of it, has the source and the destination. Okay, that's going to be the port, logical port. Okay, then that gets included into a packet, which adds lots of other stuff like the source and destination IP, as well as which protocol it's using. Any other information it needs to add, but we still have all that segment information. Okay, data frame includes the hardware addresses, so we've got the destination and source MAC. And then lastly, all of this gets converted into bits for physical transmission. All right, that pretty much wraps up today. Talked about TCP IP, talked about data encapsulation. Any questions? All right, guys, make sure you understand. Yeah. Yeah. Go ahead and end the recording here.